I believe that the results that you presented are for the case with just kinematic constraints with no kinodynamic constraints.
Yes. Yeah.
So I'm curious if like how you might extend the work to the case of dynamics. And I suppose like it might actually, it seems like some of the assumptions that you're kind of making, like the decision boundary should lie completely in the obstacle region would be different in this case. You might want to make sure to restrict the boundary to like the region of inevitable collision or something like that. Maybe you can comment on that.
Yeah, definitely one direction is extending to the dynamic case, but there is a lot of hardness in that direction right now. So for dynamic motion planning, one of the way to do that is to include all velocities, accelerations, positions into the configuration space, so that you have a much larger dimension configuration space. And then in that case, that would require more computational effort. Our framework currently, theoretically, it would work for high dimensional manipulators, but practically, it will work well up to 4 DOF right now. So that limits its application currently to dynamic case. Yeah.
Okay. So here's a question for Nils. Forgive me if I missed this, but I wonder if you can put any bounds on the regret that occurs as a function of the number of samples. Can you tell us how well it works as the number of samples increases? Can you quantify that?
Yeah, it just gets smaller. So let's say you have only one sample. You have like one shot, you have like one solution you pre-computed, and now you try to approximate either any other solution or there's an adversarial picking like the worst case thing. If you now add another sample to it, it can only get better. So your approximation can only become better, so the regret can only decrease with the number of samples.
Right, so I understand that it's monotonically decreasing.
Yes.
But the question is, can you say something about how fast?
Fast in the beginning, and then it gets slower. So that's what you usually see in the plots. Like, if the way our algorithm works is that we start with the canonical weights. So we only optimize for one feature at a time, which is not a good approximation for something that's in the middle for any like reasonable compromise. But that would be like the first thing that our algorithm would add. And then it leaves gaps between like the center point, like if it's 2D, like if the end point and the center-ish point doesn't need to be in the geometrical center. And then the next one you add is like at a largest error again. So in the beginning, you cut down the error bound quickly by just putting in the point in the most sensitive parts of your curve. And then it refines only after that. So it's, yeah.
Okay, thank you.
Have time for one more question? Or should we great talk, by the way, I really enjoyed it. So regarding implementation of what we promote, augment, is that the idea?
Exactly, and that's where you get the exponential dependence on the collision horizon. And the collision horizon is exactly how large subsets do you need. And there's a little bit of pruning that you can do, but that's the basic idea.
So the horizon is sort of a
Exactly. So the way that it's set up is that you choose the collision horizon parameter that you're going to run the algorithm with. And then every instance, you can look at the optimal solution, without computing it, and you can take its collision horizon. And the ratio between the problem's collision horizon and the algorithm's collision horizon gives you a bound on how good of an approximation it is. And if the collision horizon you ran the algorithm with is better than the problem's one, you'll get an exact solution. So we get some software degradation as the gap between the two expands.
great. Let's thank all our speakers.
Okay, great, thank you. I'm session chair for the keynote talk here. Feel free to get, these are my notes all about you. So I'm Michael Odie, I'm one of the co-chairs, and I have the privilege of being able to introduce you to Russ Tedrick. So Russ is a professor of many things, and we will get to that shortly. He's a professor at MIT, and he received his bachelor's in computer engineering from the University of Michigan, his PhD in electrical engineering and computer science from MIT. He's worked at a number of interesting places, including Microsoft Research and the Santa Fe Institute. And one of the titles that he currently holds is Vice President of Robotics Research at the Toyota Research Institute. Dr. Tedrick is one of the first roboticists that I ever personally met. Sometime back when I was a young grad student and he was a younger assistant professor. I think, as all of you know, robotics is a very wide field. And if you look at Dr. Tedrick's list of affiliations, it really reflects this fact. So he is the Toyota Professor of Electrical Engineering and Computer Science, Aeronautics and Astronautics, Mechanical Engineering, and he did a postdoc at the Brain and Cognitive Science Department at MIT. In addition to all of those affiliations, he's a director of CSAIL, and other notable accomplishments include the NSF Career Award, the DARPA Young Faculty Award in Mathematics, Microsoft Research New Faculty Fellow, and he has multiple teaching awards. Other kind of notable stuff that you're probably familiar with, but is kind of interesting to talk about, is that he spearheaded the Drake software package, and he led MIT's entry in the DARPA Robotics Challenge. This is the humanoid one. And a notable thing about that particular effort was the use of machine learning in his particular team's stuff that was in that competition. So on a personal note, I have always followed and admired Dr. Tedrick's work, and my lab's own paper here at WAFR is actually built on some of his LQR tree work from a while ago. So he's done extraordinary work in humanoid locomotion, among other things, and both at the theoretical and experimental kind of ends of the spectrum, which I think is very impressive. One of my personal favorite interactions with Dr. Tedrick was actually an exercise in applied human locomotion, which I will talk about, even though this is a kind of more theoretical conference here. And that is when he organized a small group of us to go running with him on his local commute from work home along the Charles River. And I've always wondered how much his research in humanoid locomotion and his personal experience with distance running kind of interact with each other and influence and inform each other. So I'm excited to see what he's been up to lately. It's my pleasure to introduce our first WAFR keynote speaker of 2022, Dr. Russ Tedrick.
Thank you, Michael. That was a great introduction. I really appreciate it. I'm not the director of CSAIL. That's Daniela. There's a CSAIL Center for Robotics. That's a much smaller ask. So I'm really excited to be here today because there's a set of results that we've been working on that I'd like to tell you about. And I think this is really maybe the best audience to help vet these ideas and to think about these ideas. So instead of trying to give any sort of broad coverage of the kind of things we're thinking about at the MIT group, I'm going to tell you about this one set of ideas about motion planning around convex optimization. And I'm going to take the time allotted here to try to teach you some of the details of that and step through. And I hope you'll give us good feedback and ask good questions. So in particular, there's two papers that are the 1-2 combination of work here. The first is shortest path on graph of convex sets. It's joint work with a few people. This is Pablo Perillo. Tobia is here in the audience, and you should address questions to either of us throughout the week if you have them. Okay, so the goal of the work, of course, is motion planning. I don't have to sell that to this audience. In particular, I'm interested in the questions of global motion planning and global optimization-based motion planning, in particular of systems with dynamic constraints. This is motivated for me thinking a lot about planning through contact. We want robots that can pick up objects or walk or run down the Charles, I guess. But today I'm going to actually just narrow it. We're not going to do all the way through contact today. We'll just talk about collision-free planning. And I took one of the old goody animated GIFs to say that. But also there's maybe a deeper goal for today, which is I think there's a lot of different ways that people think about planning. Maybe even in this room, there's a lot of different ways that people think about planning. You might be a trajectory optimization type person, a sample-based planning person, a logical planning person, or a combinatorial optimization expert. And to some extent, we're all talking about the same truth. And so there must be some connections here and try to I'm very interested in making some deeper connections across these different disciplines. And I hope we can give you one example of that today. And so maybe there's a litmus test of which of these you are, right? So if I think about this problem of just finding a path through a maze from the start to the goal, it's kind of interesting to see different people's reactions to this, right? So if you're a theoretical computer scientist, you think about graph theory a lot, you'd say this is a trivial problem. There's a trivial graph that lives on this. I can just do search in the graph. But if I say, okay, well, I'm actually going to fly a quadrotor through here. I want to find a continuous path through this. If you're a sample-based planning person, you say, well, I can, it's in 2D, I can sample enough, it's no big deal. If you're a trajectory optimization person, you're probably running for the hills. This is like a terrible problem for trajectory optimization on the face of it. But there are other problems, like those problems that we've been thinking about with dynamics, and they're relatively high dimensional state spaces, kinodynamic constraints. This is where trajectory optimization really shines. These one trajectory optimization recipe, you just change a few parameters. You go from running to walking to bounding, galloping, right? This is beautiful, smooth motions of a high dimensional, highly constrained system. And the sample-based planners would struggle more in this. I mean, some of you in the room have done very good work in that direction, but it always feels a little unnatural of trying to jam in dynamic constraints into the sample-based methods. So can we find something that sort of blends some of the best of both worlds? So I want to talk through that. Let's start with just thinking about the motion. I'm coming mostly from the trajectory optimization side of that. So I want to walk you through from that direction through this idea, starting with motion planning as optimization. And I'll use just a very simple example to make the point, a little running example here of moving around a red obstacle box here from the start to the goal. Because actually that's enough to make many of the key points I want to make. So let's first just think about the way that you would typically write that as a trajectory optimization problem. So we'll break it down here. So we have a cost function, which is just the sum. Well, first of all, we have a bunch of sample points that we're going to make, x0 through xn. We have a cost function, which is the sum of the squared distances, which is kind of a weird cost function, but it's a common one. Okay. We have an initial condition constraint, a final condition constraint. And then we have a collision avoidance constraint saying that for all of my samples, I'd like them to be outside the box. And in this very simple example, I can just write that as being outside the L1 ball, okay? Which is as simple as it can get for collision avoidance, but that's good enough for now. Now, this problem is clean except for this collision avoidance constraint. This is a non-convex constraint, okay? And this means that trajectory optimization based on gradients or second order kind of methods, anything that's based on local analysis of the optimization problem tends to struggle. And I'll just run a little example here to make that point. This is a little code that's running, and I've got an animated interface in the web here to do that, okay? So let's say I've got a start to the goal. To keep it super simple on the slide, I didn't worry about the segment colliding, only the points colliding. So I get a sum and nominal solution to that optimization problem just using a standard gradient-based optimization. And I can move it around. And the frustrating thing, I mean, it solves in real time, it's no big deal, even for bigger problems, okay? But the problem has local minima, right? So in particular, when I start bringing the initial condition over here, of course, there's obviously a shorter path that goes around the other side, but no matter what the system's just stuck, right? You have to get worse before you can get better if you want to hop over to the other side. It's a classic case of local minima. Okay, so let's try to fix that. And that's basically the story of the talk, is we're going to try to fix that in some fundamental way. There's one other thing that I don't like about that formulation, I've always not liked about this formulation, is this need to pick the finite number of n before you start. That's, it can be a little awkward in your optimization, but I actually think it makes the problem